Now in this video, we will be discussing another important application of transistor. That is, this transistor can be used as a switch, and any device which turns on or off electric current in electric circuit, we call it a switch. A transistor acts as a switch when it is driven back and forth between saturation region and cutoff regions. So to have a discussion on this, making use of a transistor as a switch, we will take an NPN transistor, and we will take this transistor in common emitter mode. So we have a transistor, and this is a transistor, NPN transistor. So the arrow should be out because it's NPN, and here is emitter, and here we have collector, and this is the base. And let's have some resistance, and then we have to bias it, so this must be positive, and this must be negative, and we'll join it like this. Then we will have the load resistance, or may call it collector resistance, and we'll have the biasing for output circuit as positive, negative, positive, and then this whole thing have this variable, and would like to have a voltmeter that will give us the measure of VCE here. Okay, and this is my emitter current, and can think of it as RE here, and here we have RB, and here we have RC. So let us have an output here as V out. So here we have the input. So this is basically VBE. So this is VBE, and this is my VI. So here I have the input voltage, and here I have the output voltage, and we have an NPN transistor, and it has the input circuit and output circuit, and this is the common emitter configuration of this this NPN transistor. So here we will have collector current, and here we will have the base current. Now if we look into this circuit, we can think of using Kirchhoff's voltage law for input circuit. Now before doing that, I would name this as, say, VBB, and this is certainly my V out here. Okay, so if I use KVL in the input circuit, so what am I gonna do here is we'll have this VBB equal to VBE plus IBRB. Okay, so here I'm using this. So this will be my equation for the input circuit in terms of the EMFs by making use of this KVL, and we can look for the output circuit here, and we can use KVL in output. So using KVL in output circuit. So in that case, what's going to happen? We will have this VCE. This VCE will be VCC. So this must be my VCC minus ICRC. So these are the two important equations, and if we proceed from here, So here VBB can be replaced by VI for this equation. So I can write here, so I can write VI equals to it equals to VBE. This is VBE plus IBRB. Okay, so this will be for VBB, and for this VCE, I'm going to replace it by the output voltage V out. So V out is gonna be VCC minus ICRC. So that's clear. Now let us assume that this NPN transistor is made of silicon, right? And for silicon, we know the knee voltage is 0.7 volts, and let us use that concept to understand that how this transistor and this NPN transistor works as a switch between saturation and cutoff region. So these are our equations, and to move on. So now, for the sake of argument, now if this this VI that we have, if this is equal to, say, for example, 0.6 volts, so that means it's less than 0.7 volts. So so what's going to happen in this case? The transistor will be in the cutoff region, right? So transistor will be in the cutoff region. So what's going to happen? That is, it will not conduct, and what's going to happen here is we will have IC equal to 0, right? So from this equation, from this equation, from these two equations. So what we conclude now if VI is less than VI is less than 0.7 volts, we can think in terms of the cutoff region, right? So because in this case, V out that will have that will be simply equal to VCC, right? Because IC will be 0 and V out will be equal to VCC. Clear? Now for VI, now if I take VI greater than, if I take it greater than 0.6 volts, now what's going to happen? And let me put it less than 1 volt, right? Now in this case, the transistor will be in active region. So here it's going to be in active region, right? So IC, what's going to happen with IC, collector current will be increasing linearly. So V out will be decreasing due to increase in this ICRC, right? So because in this case we can clearly understand that V out is going to decrease because IC is increasing. So V out is going to decrease for this condition, right? And now if I take this VI greater than 1 volt, now in this case the transistor will have the maximum possible collector current, the maximum possible collector current. So what's going to happen here? This ICRC, in that case, this ICRC, it will be maximum, right? So output will be least. So in that case, this V out is going to be least, right? Almost tending to 0, and practically same for all VIs in this case, for all the VIs which are greater than 1 volt, right? So it is the saturation state. So this state is the saturation state. This is the saturation state of transistor, right? Now, how we understand that this common emitter configuration of the transistor will be behaving as a switch is that when we have this base input voltage. I mean, when this base input voltage is very low, so that the transistor is not forward biased, then no current flows through RC. right? So that is, in that case, IC will be equal to 0. Hence, the output voltage is equal to VCC, right? The transistor is in cutoff mode. That is, the transistor is not conducting, and it is acting as if it is an open it's an open condition, it's an open switch off state of the transistor. Now, when this base input voltage is made sufficiently positive, the transistor is forward biased. Now, this will be a forward biased transistor. Now, the current IC will flow through this RC, right? In this situation, the voltage drop across this RC will be measured by ICRC. That will be simply equal to VCC, right? Hence, IC, if we have to measure the IC at that time, that will be VCC by RC. And VCE, now this collector emitter voltage, this is going to be equal to 0 from this equation point of view, right? So in this case, the transistor comes in a state of saturation, and the transistor acts as a closed switch, or I can say it acts in the on state. So this way, a transistor can be used as a switch in the cutoff region and in the saturation region, where one will refer to the off state of the transistor, and the other will refer to the off state of the transistor.